Welcome to Certainty, where we make assurance double sure. In this video, we are going to look at linear regression using the least square method and test the linear model using analysis of variance. Many problems in engineering and the sciences involve a study or analysis of the relationship between two or more variables. For example, the pressure of a gas in a container is related to the temperature. The velocity of water in an open channel is related to the width of the channel, and the displacement of a particle at a certain time is related to its velocity. If we let d be the displacement of the particle from the origin at time t equals 0 and v be the velocity, then the displacement at time t is d equals d naught plus v. With this formula, we can predict displacement perfectly. However, there are many situations where the relationship between variables is not deterministic. The collection of statistical tools that are used to model and explore relationships between variables that are related in a non-deterministic manner is called regression analysis. In this chapter, we present a situation where there is only one independent variable x, and the relationship with the response I is assumed to be linear. Therefore, we assume random variable y is related to x by the straight line relationship y equals beta naught plus beta 1 times x. Beta naught is the intercept of a line, beta 1 is the gradient, and e is a random error term. Let's look at an example. A sample of 6 pieces of wet metal rods of the same weight were dried in sunlight for different amounts of time. The dry weight of metal rods, y, is believed to be related to the exposure time to sunlight x through the model y equals beta naught plus beta 1 times root x plus an error term. The following data were obtained. Fit a simple regression model to these data using the least square method and test the significance of this model. Normally, our equation should inform of y equals beta naught plus beta 1 times x, but this time we have root x. What we have to do is to change the variables. We want the value of beta naught and beta 1, which are also known as regression coefficients. We have formulas for beta naught and beta 1. Beta 1 equals sxy over sxx. Beta naught is I bar beta 1 x bar. But what are sxx and sxy? Sxx is obtained by saying the summation of x squared minus the square of summation of x over n. Sxy is the summation of xe minus the product of the summation of x and the summation of I over n. Now let's transform root x to x star. To compute linear regression, we can use software such as Excel, RRE, or work physically without software, which is what we are going to do. Let's write in column form. Let's add root x column and the it. I am not going to simplify in order to obtain exact values. Now take your calculator. I'm using sharp right view, but the type doesn't matter. Now press mode and choose stat, then go to line. Fill the table for y values and for x value put root x values. For example, 132 on y corresponds with root 90 on x. When you are done, press alpha or simply press recall. Now let's write down calculated values. Press recall sum of I, recall sum of x, recall sum of xe, recall sum of x squared, n is 6, recall sum of x bar, and finally recall sum of I bar. Now we can find sxx and syy by plugging in the calculated values into our formula. Let's find beta 1 by dividing sxy by sxx and beta naught by this formula. Remember to take note of the signs. Negative and negative give us positive. We now have our coefficients. Let's write our final formula. Remember, x star is the root. If you're enjoying this video, support us by liking, sharing, and subscribe. Now let's test the significance of the model. We are using ANOVA, which is short for analysis of variance. You can use t-test if you want. That won't affect the answer. The procedure partitions the total variability in the response variable into meaningful components that form the basis for the test. We use variance identity. The two components on the right-hand side measure, respectively, the amount of variability in III accounted for by the regression line and the residual variation left unexplained by the regression line. SST stands for total corrected sum of squares, SSR for regression sum of squares, and SSE for error sum of squares. SSE equals I minus y hat all squared, SSR equals y hat minus y bar all squared, and SST equals I minus I bar all squared. As you can see, SST equals SSA plus SSR. The total sum of squares, SST, has n minus 1 degree of freedom. SSR and SSE have 1 and n minus 2 degrees of freedom, respectively. I bar is the average of all I values in the observed data. I minus I hat gives us the individual error of prediction, while I hat minus I bar pertains to the variation in the estimated values compared to the average. Now let's go to the ANOVA, a formula test for the significance of regression. It is given by F naught equals SSR over 1 divided by SSE over n minus 2, which can be simplified to MSR over MSE. The quantities MSR equals SSR over 1 and MSE equals SSE over n minus 2 are called mean squares. The null hypothesis is rejected in an analysis of variance when the p-value is less than the significance level, or when the f-test statistic is greater than the f-critical value. Remember that alpha is the level of significance. Now let's draw the ANOVA table. The first column is for the source of variation. The second column is for the sum of squares. The third column is for mean squares, and the last is for F naught. The last row is the total raw. Don't get confused by the second column. Those are alternative formulas for SSR and SST. That's what we will be using for ANOVA. We use the F distribution table. Let's start our test procedure. First, let's write the formula for SST. This is the same as the summation of I squared minus ny bar squared. SST. Let's write the alternative formula for SSE and SSR. Now we can sub SSR into this above formula to get SSR plus SSSE equals SST. We need a summation of I squared and I bar squared. We can recall the sum I from our calculator and square the answer. We will do the same for I bar. We know that n equals 6. Instead of listing I term, I bar terms, and y hat terms, we are going to use a short method. We will use the correlation coefficient from our data by simply pressing recall R or alpha R. SSR equals R squared times SST. This will save us time than trying to compute SSR, SSE, and SST using primary formulas. Now we need SST or SSR to solve a simple equation. Let's use SST. We have I squared n and y bar squared. If we simplify w, get 8163.5. Now let's sub SST into our formula and find SSR. Using SST equals SSR plus SSE, we can make SSE the subject of the formula. Now SSE is 299.243. Now we have all we need. Let's draw our table. Now let's fill it. N is 6. Let's calculate MSE by dividing SSA by n minus 2. Since MSR is SSR over 1, we will just put SSR. Finally, let's calculate F note. Our null hypothesis is that beta 1 is 0, meaning there is no relationship between y and x. The alternative hypothesis is that beta 1 is not equal to 0, meaning there is a relationship between x and y. You can also do the test for the intercept. Let's use a significance level of 0,005. From our calculation, F naught is 105.26. We only reject the null hypothesis if F naught is not greater than the p-value. Now let's look at our F distribution table. We want the intersection of 1 and 4 and make sure that alpha is 0,005. The answer we get is 7.71, which is less than F naught. This means we have enough evidence to reject the null hypothesis, meaning there is a relationship between y and x. Thank you for watching. Don't forget to subscribe.